Okay, so let's look at our first lecture in this series. Um, we have electrostatics, conductors and insulators, electric charge, method of charging, properties of electric charge. So when you hear the word electrostatics, there are two words there, electro and statics. Electro, that is taken from charges or electrons, but put it as charges. Then statics, stationary position. So apparently what electrostatics means is charge at rest. So electrostatics is the study of charges at rest. So the study of electricity, the study of charge, static electricity, that is electrostatics. When the charges are not at rest, when the charges are moving from one point to the other, they constitute electric current. So that is where our electricity, current electricity comes from. But when the charge is at rest, there is no current that is generated. Only when the charge is moving, that is when current is generated. So the behavior of an object that has been charged is dependent upon whether the object is made of a conductive or non-conductive material. Now, materials can be divided into three categories. We have, number one, the conductors. Conductors have excess electrons in them, and so they allow easy flow of electrons from one point to the other, or current to flow through them, or heat to flow through them. That is conductors. Then the second categories of materials are semiconductors. Like the word implies, semi means they are between conductors and insulators. They behave like insulator when the temperature is 0 degree, and behave like a conductor when the temperature is at room temperature, 25 or above. But then you have to be careful not to increase the temperature beyond a certain level. Otherwise, it will give a negative temperature coefficient. So that is semiconductor. And the last category, like I mentioned, is insulators. Insulators are materials that do not conduct electricity and heat. Now, an object made of a conducting material will permit charge to be transferred across the entire surface of the object. So if I have a conductor and I introduce a charge at one aspect of the conductor, because of his ability to allow charges to move from one point to the other, that charge is transferred across the entire surface of the object. In our layman language, we can say something that is generous. Something that is generous. That is, you have something and you are not keeping it to yourself. You are giving it out to every other person. You are sharing it to other people around you. That is a generous person. Whereas insulators are stingy people. If you are stingy, you are an insulator. So insulators are material that impedes the free flow of electrons from one atom to the other. When charges are transferred to an insulator at a given location, the charge that was transferred to the insulator remains at the initial location of that material. The charges are not distributed across the insulator, unlike conductors who allow charges to be distributed across it. Insulators do not allow charges to be distributed across it. Examples of conductor are copper, iron, and steel. Examples of semiconductors are germanium, silicon. And examples of insulators are plastic, wood, glass, rubbers. Now, what is an electric charge? An electric charge is a basic property of matter carried by some elementary particles. Basic property of matter carried by some elementary particles such as electrons and protons. Now, how do we know an electron? We know that an electron is charged negatively. And then a proton charges that the elementary particles carries. That is the electron and the proton carries is what we refer to as charges. So charges are physical properties of matter that causes it to experience a force when kept in an electromagnetic field. So it's this charge that is so I was saying that it is a charges are physical properties of matter that causes it to experience a force when kept in an electromagnetic field. So when charges are placed in an electric field or in a magnetic field, the force they feel, that is being attracted to one another or repel one another, is as a result of that the charge that the elementary property of matter carries. So we have two kinds of charges. We have positive and negative charge, positive and negative charges. Now, coming to electric charge in an atom. An atom is made up of nucleus and energy shells. Nucleus and energy shells. In the nucleus, we have the nucleus is domiciled at the center of the atom. And there we have the proton, which is positively charged, and then the neutron, which is neutral in nature. Neutron does not have charge, only the proton has charge. However, they both possess masses. The neutron has mass equivalent to the mass of proton. The mass of a neutron is 1.67 times 10 raised to minus 1.67 times 10 raised to minus 27 kilogram, while the mass of a proton is also 1.67 times 10 raised to minus 27 kg. The electron revolves around the nucleus in an elliptical or circular manner. The mass of the electron is 9.1 times 10 raised to minus 31 kg. That is the mass of electron. However, the magnitude of the charge on an electron is equivalent to the magnitude of a charge on a proton. So electron carries negative charge, proton carries positive charge. Their magnitude are the same, positive and negative. So atom basics. Atom is said to be electrically neutral because it has equal number of positive protons and negative electrons. The number of electrons in an atom that is neutral, electrically neutral, is equal to the number of protons. And because the charge they carry, positive and negative, are of the same magnitude, so that is why the atom is electrically neutral. An object is said to be charged when it has an equal amount of positive and negative charges. So when the number of positive and negative charges are equal, are balanced, the atom is electrically neutral. If there is deficiency, if they are not balanced, if either positive charges are higher a number than negative charges in an atom, or the negative charges are more than the positive charges in an atom, that atom or that object or material will be said to be charged. And the charge it carries will be the charge that is more. So for instance, when we say that an object is positively charged, it means that the number of positive charge on that object is more than the number of negative charge. If we say an object is negatively charged, it means there are more negative charges than positive charges in that object. So now you should know that protons, that is positive charges, do not move from one point to the other. Only electrons moves from one point to the other. And the movement of electron from one point to the other is what constitutes electricity, electric current. So when an object gains or loses electrons, it becomes charged. When an object gains or loses electrons, it becomes charged. So if it gains electrons, it means that the object has more electrons. So the object becomes negatively charged. If it loses electrons, it means that the positive charges in that object will become more than the negative charges. So that object becomes positively charged. If there are more positive charges in an object, the object is positively charged. If there are more negative charges in an object, the object is negatively charged. If the same amount of positive and negative charges if we have the same amount of positive and negative charges in an object, the object is neutral. So note that, very important. Now, how do we charge? Now, if we rub a balloon on our clothes and move it close to a wall, it sticks to the wall. If we also comb our hair and move the comb over a piece of paper, or if we rub our clothes or our hair with our pen, the pen in our hand, and move it over a small piece of paper, it will pick up the paper. This is because the pen is charged. So since it's charged, when you move it over a piece of paper, which is neutral, there will be what we call polarization of charges. There will be an attraction. Charges will separate, like charges will repel, unlike charges will attract, and then the object becomes charged. So we'll talk more on that, on polarization of charges later. So fundamental laws of charges. Unlike charges attract, while like charges repels. So if you look at that diagram on the left with red and at the center with blue, the one with red color has a positive charges. Both are positively charged. And then the one with blue at the center, both are negatively charged. Because they have the same charge, they repel, they move away from each other. That is why you see the arrow moving apart. Then the last diagram by the right, you see we have a blue rod and a red rod. The blue has a negative, the blue is negatively charged, the red is positively charged. So when we move them close together, they attract. That is why you see the two arrows moving together. So they attract. Now, this attraction and repulsion between charged particles is called an electric force. They attract by a force. Something pulls them together. It's a force that pulls together. And then they repel. They are pushed back. So something is pushing them back away from each other. That is repulsion, force of repulsion. Remember that force can be defined as a push or a pull on an object. So when two things are pulled together, there is an attractive force. When they are pushed away from themselves, that is a repulsive force. So a positive and a positive will repel, a negative and a negative will repel, but a positive and a negative will always attract. Now, method of charging. We have said that charging simply means gaining or losing electron. So when material loses electron, it is positively charged. When material gains electron, it is negatively charged. And if the number of electron gained by a material is equal to the number of electrons lost by the other material, that we should also know. The number of electrons gained by a material is always equal to the number of electrons lost by the other material. We'll come back to this, the last one there, the last statement I just made, which has to do with conservation of charges. Under conservation of energy, which is popular to most students, we know that energy cannot be destroyed nor created, but transformed or converted from one form to another. The same thing applies here too. Charges cannot be destroyed, cannot be created, but can be transferred from one object to another object, or from one body to another body. So method of charging, we have three types of charging, method of charging. Number one is charging by friction. Charging by friction simply means rubbing against one another, like the previous example I stated or mentioned, where you rub your hair with your pen. That is rubbing. Your pen is plastic. Your pen is an insulator. Your hair is also is like a silk. It's an insulator. So they are not conductors, they are insulators. So when you want to charge insulators, you rub them. You charge them by rubbing them or by friction. Now, the second method of charging is by contact. You bring a charged body in contact with an uncharged body. The third method of charging is by induction. You move a charged body close to an uncharged body, close to a neutral body. So we are going to treat them one by one. charging by friction. When two neutral bodies are rubbed against each other, one object may pull electrons away from the other, creating one positive object and one negative object. This is known as charging by friction. This charging takes place in an insulator only. Example, when a glass rod is rubbed with a silk cloth, glass acquires positive charge and the silk cloth acquires negative charge. Now, if you look at this example here, glass acquires positive charge and silk acquires negative charge, which means that glass will transfer electrons to the silk, because when an object loses electrons, it becomes positively charged. And when an object gains electrons, it becomes negatively charged. So in this example, glass is losing electrons and silk is gaining electrons. And when you take the conservation of charges, the amount of electrons lost by glass is the amount of electrons gained by silk. So that is how to charge two insulators. One becomes positively charged, the other one becomes negatively charged. Another example, there is an ebonite rod rubbed with four cloth. Ebonite rod here acquires negative charge and four cloth acquires a positive charge. So in this case, the four cloth loses electrons to the ebonite rod. So the ebonite rod gains electrons and becomes negatively charged, while the four cloth that loses electrons become positively charged, because the proton, which are the positive charge, will be more in that four cloth than the electrons. So a third example here is rubbing your cloth with a balloon. So when you rub your cloth with a balloon and then move it close to the wall, it sticks to the wall. So your cloth, just like the ebonite rod, rubbed with four gives out electrons. Ebonite rod became positive, and four became positive. Ebonite became negative, four became positive, because the cloth loses electrons. So the same thing here applies. The cloth, electrons on the cloth is transferred to the balloon, which means that the cloth will become positively charged, while the balloon will become negatively charged. Now, your wall is neutral. That is, it has equal amount of electrons and proton, equal amount of positive and negative charges. So it is neutral. It is neutral. So if you now move the cloth, if you move the cloth close to the wall, there is what we call separation of charges. There will be separation of charges. That is what we call polarization. Because the balloon is negatively charged, the wall has both positive and negative charges. So the negative charge on the balloon will push all the negative charge on the wall to the other side and attract all the positive charges to the side of the balloon. So now we have positive and negative charges facing themselves. So what will happen? Attraction. So that is why the balloon sticks to the wall. Now, charging by contact. Charging by contact. Charging by contact or conduction involves the contact of a charged object to a neutral object. When you want to charge an object, let's say the object is neutral, and you want to charge it positively. You want to give it a positive charge. You want to make it a positive charge. You bring a positive charge object in contact with it. When you bring a positive charge object in contact with it, remember what I explained before, there will be polarization of charges. So because the charge body, okay, let me use the marker. So this is a neutral body. We want to charge this positively. We want to give this a positive charge. So what we should do now is by charging by contact, we bring a positively charged rod in contact with the neutral body. So when we do that, there will be separation of charges, polarization of charges. Because this charge rod is positive, it will repel all the positive charges to this side, to the other side of the neutral body, and attract all the negative charges to this other side of the neutral body. So when that separation happens, remember that electrons are the ones that moves. Proton does not move. So now, in this case, the electrons will be attracted into the charge body, into this charge body. All the electrons from the neutral body that have separated from the other one will be attracted into this charge body. And then by the time you remove them, which is the third diagram, the positive charges are the ones that will be left in that object that initially was neutral. So that is how to charge an object by method of conduction or contact. So if I want to charge a body positively, it means that I must bring a charge body that is already positive in contact with it. Note that. So if you want to charge a body positively, you bring a body that is already charged in contact with it. So let's move to charging by induction. So to charge by induction is a method used to charge an object without actually touching the object to any other object. So this time, the charge body brought close to the neutral body is not making physical contact. You just move it close to the neutral body. You bring the charge body close to the neutral body. Here, the charge body is the red, charged negatively. The two objects that are to be charged, A and B, are neutral. So when we move a charge body close to uncharged body, a neutral body, there will be polarization of charges. So because this charge body is negative, it will attract, when polarization of charges takes place, all the positive charges will come to A, while the negative charges will be repelled to B. So when that happens, and then we separate them, in diagram 3, we have separated A and B. So now A is positively charged, B is negatively charged. So by the time we finally remove the charged body, which is the red object there that you are seeing in diagram 4, we see that A is positively charged and B is negatively charged. So that is how to charge a body by induction. That is by bringing a charged body close by, not touching it, but just close by. So I've talked about this before, polarization of charges. A polarization in the process of is the process of separating opposite charges within an object. If you look at this diagram here, for every neutral body, we have equal number of neutron, equal number of proton and electron, equal number of positive charges and negative charges. So this has equal number of positive and negative charges. Now, if I want a process of polarization, polarization is when the charges are separated. Negative charges here and then positive charges here. They are separated within the system. Now, that is led by or caused by bringing either a negative charge here or bringing a positive charge here. If I bring a positive charge object here to the left side, all the negative charges will move to that side. And if I bring a negative charge to the right side, all the positive charges will move to the right side and push the negative charge back because of the fundamental laws of charges. Light charges attract, light charges repels, while unlight charges attract. Light charges repels, while unlight charges attracts. So that is polarization of charges. Now, properties of electric charges. Charge, as we know, is a scalar quantity. It has only magnitude and no direction. Only magnitude and no direction. So what are the basic properties of charges? 1, additivity of charges. 2, conservation of charges. 3, quantization of charges. So what is additivity? Additivity is taken from the word addition, which implies that we add them, we can add them together. We can add the charges together. So charges are additive. We can add them together. So for instance here, we have an example here where a system has 3 column, positive 3 column, 2 column, 5 column, and minus 4 column. So if we are asked to find the net charge, that is the total sum of charge of that system, that will be plus 3 plus 3 plus 2 plus 5, that is 10. 10 minus 4. So the total charge in that system will be 6 coulomb. 6 coulomb. So charges are additive in nature because they are scalar quantity. We can add them directly. If a system contains charges, we can just add them, find the sum of the net charge of that system by adding all the charges that is contained in that system. So let's look at the second property, which is conservation of charges. I've explained this before. The amount of charge lost by a body is the same amount of charge gained by another body. When two bodies rub against themselves, one body loses charge, electrons, while the other body gains electrons. So the amount of electron lost by one body is equal to the amount of electron gained by the other body. If we add them together, it will all, before the two bodies interact, the total amount of charge will always equal to the total amount of charge after the two bodies interact. So that is conservation of charges. Conservation of charges. And the third property of charges are quantization. So quantization of charges means that the charge of any object is an integer multiple of the elementary charge. The elementary charge here is the electron. It is an integer multiple. That is a whole number multiple. So it's given as Q is equal to NE, where Q is the charge of the body, N is the number of charge contained in that body, and then E is the electron charge. Electron charge is a constant value, 1.6 times 10 raised to minus 19 coulomb. So all charges comes in multiple of the elementary charge. So we can have one charge, two charges, three charges, minus three charges, minus five charges, and so on. We cannot have 1.5 charge or 3.2 charge, 3.8 charge. We cannot have irrational number. They must be an integer. So that is what quantization of charge is about. So these are some constants that you need to know while studying electrostatics. So if you're watching, and you have not subscribed, kindly subscribe so that subsequent class, you will just be prompted. Right. So for electron, the electric charge is 1.602 times 10 raised to minus 19 coulomb. Proton has the same amount of charge. Like I told you before, that the magnitude of the charge on an electron is equal to the magnitude of charge in a proton. When we talk of magnitude, we ignore the plus and minus. We only deal with the number, the value. So if you look at the values for proton and neutron under electric charge, you see that they are the same, 1.602 times 10 raised to minus 19 coulomb for proton and neutron. The only difference between them is electron is negatively charged, while proton is positively charged, but they carry the same amount of charge in magnitude. And then the mass of proton is 9.109 times 10 raised to minus 31 kg, while the mass of proton is 1.673 times 10 raised to minus 27 kg. Mass of neutron is 1.675 times 10 raised to minus 27 kg. So the mass of proton and mass of neutron are approximately equal. Proton is 1673. Neutron is 1675. So if we can say they are approximately equal. Neutron, however, does not have a charge. It is neutral. Now, earthing and grounding. In electricity, the ground is very important. This is generally a huge body that will be electrically neutral. So the earth is a great example of ground. The human body can also serve as a ground for many cases. Earthing is the process of sharing charges with the earth or ground, it provides a safety measure for electrical circuits and appliances. A safety measure for electrical circuits and appliances. In our home, we have sockets. If you look around, maybe your room in your home, you have your sockets this way. Always come in this way. So this could be the life, this could be the neutral, but this is our earthing. This is our earthing or our ground. So what this does is when there is a surge, that is a sudden high voltage coming into the house, sometimes through lightning, through thunderstorm, or when there is a supply of power to the house and all of a sudden the supply comes in unexpected surge. It is with the help of this pot, earthen pot, that the unwanted, unexpected, the excess voltage will go out through this earthen pot. That is why it is very important for houses to be earthed. If the house does not have a very good earthing facility, though the excess voltage will go into our appliances and then destroy all the appliances. But if the house has a very good earthing system, it will follow through this part and go straight into the ground, into the earth, and appliances will be protected. So that is why it's very important that our houses are properly earthed. So our body can also serve as earthing or ground. For instance, when we charge this negative charge, this by induction, a negatively charged object is brought close to a neutral body. Now, when that happens, there will be polarization of charges. All the positive charges, you see all the positive charges here, and the negative charges here. So now, the next diagram there, you see diagram 3. You see the hand touching the body. So when the hand touches this body, is all the negative charges will flow through the hand into the ground. So the earth there, the hand there, the human body there has served as earthing. So the excess charge, the charges that are not wanted, flows through the hand into the ground. And then we have our positively charged system there. So our human body also could serve as earthing, but don't try it. Don't go and hold any naked electrical cable, live electrical cable, because it could be dangerous. So the gold leaf electroscope. Gold leaf electroscope is an instrument for detecting the presence of a charge, also used to determine the polarity and the magnitude of charges. So if I want to know if there are charges somewhere in a particular environment, the gold leaf electroscope is an instrument that can tell us that there are charges here or not. If I want to know the polarity of charge, that is, whether the charge is positive or negative, is the gold leaf electroscope that will tell me if the charge is positive or negative. And if I want to know the amount, the size of the charge that is present, the gold leaf electroscope is also an instrument that can tell us the magnitude of the charge. So here we have a, a well-labeled diagram of a gold leaf electroscope. So we have the metal cap, we have the insulator, we have the conducting case, we have the stem, the gold leaf, we have the earthen terminal, and the glass front. The glass front. So we can charge using the gold leaf electroscope by applying method of charging by contact as well as method of charging by induction. Remember, method of charging by contact will give me the same charge. So here I have a negatively charged rod placed on the cap of the metal cap of the gold leaf. Now the gold leaf, at the end of it, the gold leaf will be charged negatively. If I want to charge an object positively, I can use the induction method. That is opposite charging. I can use the induction method. So this time I brought a negative charge close to the gold leaf, the metal cap of the gold leaf, and then I earthed the gold leaf. So by earthing, it means that all the negative charges in the gold leaf will move through the earthing into the ground, leaving only positively charged in the gold leaf. So here are some exercises. So we have here a neutral metal sphere is touched by a negatively charged metal rod. As a result, the sphere will be what? And the metal rod will be dash. Select the two answers in their respective order. So if a neutral metal rod is touched, that is by contact, by a negatively charged metal rod, the metal sphere will become what? And the metal rod will be what? At the end of the charging process. So this is a case of charging by conduction or charging by contact. When a charged object is used to charge a neutral object by conduction, the previously neutral object acquires the same type of charge as the charged object. So the charged object maintains the same type of charge that it originally had. So in this case, both objects have a negative charge. Both objects have a negative charge. Remember, I told you that when you are charging by contact, you are going to have the same charge on both charging object and the neutral body. Now, a neutral metal sphere is touched by a negatively charged metal rod. During the process, electrons are transferred from dash to dash, and the sphere acquires a dash charge. So what is your answer? a neutral metal sphere is touched. So this is also charging by conduction. Both objects acquire the same type of charge. So if a negative object is used to charge a neutral object, then both objects becomes charged negatively. In order for the neutral sphere to become negative, it must gain electrons from the negatively charged rod. So our answer is C. The first one, our answer is B. The second, our answer is C. Charge rod, neutral sphere, negative. Now, the third exercise, a neutral metal sphere is touched by a positively charged metal rod. During the process, protons are transferred from dash to the dash, and the sphere acquires a dash charge. What should be our answer? Our answer here is E, because proton, like I told you, positive charges do not move. It's only negative charges that moves from one point to another. So gaining electron or losing electron is what makes an object to be charged. So the statement saying protons are transferred is nonsense. So our correct answer is E. A metal sphere is electrically neutral. It is touched by a positively charged metal rod. As a result, the metal sphere becomes charged positively. Which of the following occur during the process? List all that apply, which means that you can choose A, B, C, D, E, or A, B, or A, B, C. You can choose as many of them that apply. That have the correct answer. So in electrostatics activity, protons are never transferred, which rules out choice A and E. So since A and E are to do with proton transferred from the rod to the sphere, those two are out of it. Let's look at the next B, C, D. Electrons are transferred, fine. The metal sphere loses electron, correct. The overall charge of the system is conserved, correct. So we have B, C, D. The amount of charge that is lost is equal to the amount of charge that is gained. So that is D. So the answer is B, C, D. So I will leave the rest of the exercises to you. I'll go through them, and in the comment section, write your answer. In the comment section, write your answer. Now, look at this last one. I'll give you a clue, but you have to solve it. A polyethylene piece rubbed with wool is found to have a negative charge of 3 times 10 raised to minus 7 coulomb. Estimate the number of electrons transferred, and then tell us from which to which of them, from where to where. And then, is there also mass transfer from wool to polyethylene? I will just give you a clue. You remember that under quantization, there is a formula. So if you can't remember, go back to quantization, use that formula. That formula will guide you. So that is Q is equal to NE. So this formula will guide you how to solve it. Where Q is 3 3 times 10 raised to minus 7 coulomb. E is equal to 1.6 times 10 raised to minus 19 coulomb. So if we have Q is equal to NE, it means that N will be equal to Q over E. So that will give us the number of N. Now remember that your N must be integer. So whatever answer you get must be approximated to a whole number. Your N cannot be 1.2 or 2.5. It must be a whole number. So all the best. See you in the next class.